Welcome to G Fun Facts Online. Today, we are going to talk about time. Not just the time you see on your phone or the watch on your wrist, but the fundamental definition of time itself. For decades, humanity has marched to the beat of the atomic clock, a device so precise that it would only lose a single second every few 100 million years. It is the gold standard of metrology. It is the heartbeat of our GPS systems, our internet, and our global financial markets. But in September 2024, in a quiet laboratory at GILA, a joint institute of the National Institute of Standards and Technology and the University of Colorado Boulder, that ceiling was shattered. A team of physicists didn't just build a better atomic clock. They successfully demonstrated the core technology for a nuclear clock. This is a massive leap forward. It is a paradigm shift from measuring the dance of electrons on the surface of an atom to measuring the heartbeat of the atom's dense protected core. This breakthrough promises to revolutionize everything from deep space navigation to our understanding of the fundamental fabric of the universe. So let's dive deep into how they did it, why it matters, and what this means for the future of science. To really understand the magnitude of this achievement, we first have to look at the history of timekeeping. For the vast majority of human existence, time was astronomical. We looked at the rotation of the Earth to define the day. We looked at the Earth's orbit around the Sun to define the year. We built sundials, water clocks, and eventually mechanical pendulums to slice these celestial cycles into manageable human increments. But there is a problem with using the Earth as a clock. The Earth is actually a terrible timekeeper. It wobbles on its axis. It slows down due to tidal friction caused by the Moon. It is geologically alive and inconsistent. In the 20th century, scientists realized that to measure the universe truly, we needed a reference that was immune to the chaotic vagaries of planetary motion. We needed something universal, immutable, and identical everywhere in the universe. We found that constant in the atom. Current atomic clocks work by measuring the frequency of electrons jumping between energy levels in an atom. The standard today uses cesium-133. Here's how it works. When you expose a cesium atom to microwave radiation at a very specific frequency, specifically 9,192,631,770 Hz, its outermost electron makes a quantum leap between two hyperfine energy states. We define 1 second as exactly that number of oscillations. This tick is incredibly stable because it is determined by the laws of quantum mechanics, not by rusty gears or metal springs. However, even atoms have their flaws. The electrons that we measure in these clocks orbit far from the nucleus. This makes them sensitive to the outside world. They can be affected by stray electromagnetic fields, temperature fluctuations, and collisions with other atoms. To keep today's best optical atomic clocks accurate, physicists have to go to extreme lengths. They must trap individual atoms in vacuum chambers, cool them to near absolute zero with lasers, and shield them heavily from the environment. We basically hit a wall. To get more precise, we needed a pendulum that was naturally protected from the noise of the world. And that is where the nuclear clock comes in. The nucleus of an atom is about 100,000 times smaller than the electron cloud that surrounds it. It is held together by the strong nuclear force, which is the most powerful force in nature. Because it is so small and so tightly bound, the nucleus is naturally shielded from external interference. Stray magnetic fields and thermal noise that would send an electron spiraling off course barely register to the nucleus. Think of it this way. An electronic atomic clock is like having a pendulum swinging on a windy front porch. It is accurate, but the wind affects it. A nuclear clock is like moving that timekeeping pendulum into a deep, concrete-lined underground bunker. It is fundamentally more robust. A clock based on the ticking of a nucleus, which means switching between nuclear energy states, would be orders of magnitude more precise than any electronic atomic clock. So if the nuclear clock is such a great idea, why haven't we built one before? The problem is energy. In almost every element in the periodic table, the energy required to excite a nucleus is absolutely enormous. To get a nucleus to tick, or jump energy states, you typically need high-energy X-rays or gamma rays. We simply do not have lasers that can produce coherent X-rays with the control needed for a clock. We cannot just tune a gamma ray burst like we tune a radio. For decades, the nuclear clock remained a theoretical dream because the energy key required to wind it was too heavy for us to lift. This is where nature gave us a gift. Enter Thorium-229. Among the thousands of known isotopes, Thorium-229 is a complete anomaly. It possesses a nuclear excited state, known as an isomer, that is tantalizingly close to its ground state. The energy difference is not measured in kilo-electron-volts or mega-electron-volts like other nuclei. It is a mere 8.3557 electron-volts. This is shockingly low. It corresponds to the energy of ultraviolet or UV light. This is the crucial distinction because humanity has developed lasers that operate in the UV range. Thorium-229 is the only nucleus known to science that can be excited by a laser. It is the only keyhole in the nuclear fortress that we can reach with our current technological keys. The existence of this state was predicted nearly 50 years ago, but finding the exact frequency was a scientific needle in a haystack search that spanned decades. Because the transition is so narrow and specific, you have to hit it with exactly the right color of UV light. If you are off by a fraction of a nanometer, absolutely nothing happens. For years, researchers at institutes like LMU Munich, TU Wien, and Gila circled the target. In 2016, they got the first direct detection of the decay, confirming it existed. By 2023, researchers finally measured the energy well enough to know roughly where to aim their lasers. And then, in September 2024, we got the breakthrough. The experiment that made headlines involved a collaboration between the Vienna Center for Quantum Science and Technology and Gila. Unlike traditional atomic clocks, where atoms float in a vacuum, the team used a solid-state crystal. They took a crystal of calcium fluoride, which is a transparent, durable material, and they doped it with billions of Thorium-229 nuclei. This is a huge advantage. Because the nucleus is so insensitive to its environment, the crystal lattice, which would ruin a normal atomic clock, does not disturb the nuclear tick. It allows for a solid-state device, essentially a clock on a chip. Here is the setup they used. They placed a fingernail-sized crystal containing the thorium in the path of a laser. To hit the ultra-precise UV note required to excite the thorium, the team used a frequency cone. This device, invented by Nobel laureates including JILA's own Jan Hall, acts like a ruler for light. It creates hundreds of thousands of perfectly spaced laser frequencies. They then linked this setup to one of the world's most precise existing clocks, the Gila strontium lattice atomic clock. The strontium clock provided the stable reference ruler, and the frequency comb converted that stability into the UV light needed for the thorium. Then came the eureka moment. The researchers scanned their UV laser across the predicted frequencies. Suddenly, the thorium nuclei responded. They absorbed the light and jumped to their excited isomeric state. The team had successfully established a frequency link between a standard atomic clock and the nuclear transition. They measured the frequency of the thorium tick with unprecedented precision. The number they found was 2,020,407,384,335 kHz. While this prototype is not yet a standalone clock, because it currently relies on the strontium clock to keep the laser steady, it proved the concept works. It demonstrated that we can drive a nuclear transition with a laser and count the ticks. Now you might be asking, why does this change everything? Why do we need a clock this precise? A fully operational nuclear clock offers advantages that go far beyond just knowing the time better. The first major application is unmatched precision and stability. While the best atomic clocks might lose a second every 30 billion years, a mature nuclear clock could theoretically run for the age of the universe without losing a beat. This stability is crucial for deep space navigation. Currently, spacecraft rely on signals sent from Earth to determine their position. As they get further away, that delay creates errors. A nuclear clock is robust in solid state. It is literally a crystal chip. This means it could be put on a spaceship. A spacecraft with its own nuclear clock could navigate autonomously to the edge of the solar system with millimeter precision. It would revolutionize how we explore the cosmos. The second major implication is the search for dark matter. This is where the physics gets really wild. We know dark matter exists because of its gravitational pull on galaxies, but we have never detected it directly. Some theories suggest that dark matter might interact with ordinary matter not just through gravity, but through tiny, subtle shifts in the fundamental constants of nature. Because the thorium transition is determined by the interplay of the strong nuclear force and electromagnetism, it is incredibly sensitive to changes in these forces. If a wave of dark matter passed through the Earth, it might jiggle the tick of a nuclear clock in a way that differs from an electronic atomic clock. By comparing the two clocks side by side, we could turn the nuclear clock into a dark matter detector. Third, we have the question of the fundamental constants themselves. Physics relies on numbers like the fine structure constant, often denoted as alpha, which determines the strength of the electromagnetic force. We assume this number is fixed everywhere in space and time. But is it? Some theories of the early universe suggest it might drift over billions of years. A nuclear clock is roughly 10,000 times more sensitive to changes in the fine structure constant than an atomic clock. By monitoring the ratio of the nuclear tick to the electronic tick over a few years, scientists could test the stability of the universe's fundamental laws with accuracy never before possible. Finally, there is the field of relativistic geodesy. Einstein's theory of general relativity tells us that time passes slower closer to a massive object due to gravity. This means a clock on the floor literally ticks slower than a clock on a table. Current atomic clocks are sensitive enough to detect a change in height of about 1 centimeter. A nuclear clock could be sensitive enough to detect height changes of less than a millimeter. This would turn the clock into the ultimate sensor for Earth sciences. We could measure the lifting of continents in real time. We could detect the swelling of magma chambers before volcanoes erupt. We could monitor rising sea levels with microscopic accuracy, all by measuring the warping of time itself. We are not quite at the finish line yet. The device built in September 2024 is a prototype. It successfully excited the nucleus and measured the frequency, but it hasn't yet closed the loop to run autonomously as a clock. The next steps involve improving the lasers. Scientists need to develop portable, ultra-stable UV lasers that can lock onto the thorium frequency without needing a room-sized strontium clock as a guide. They also need to refine the crystal purity. Better calcium fluoride crystals will ensure the thorium nuclei are perfectly arranged, maximizing the signal clarity. And they need to work on cooling. While the nucleus is shielded, cooling the crystal further will reduce remaining thermal noise, pushing precision to the theoretical limit. The transition from the pendulum to the quartz crystal gave us modern electronics. The transition from quartz to the atom gave us GPS and the internet. The transition from the atom to the nucleus promises to give us a window into the deepest mysteries of physics. The thorium transition is no longer just a dot on a chart of isotopes. It is a working machine. We have successfully picked the lock of the atomic nucleus, and inside, we found the rhythm of the universe. The world's first nuclear clock is no longer science fiction. It is an engineering challenge, and the countdown has already begun. Thanks for listening to G Fun Facts Online.